Now let's move on to covariance and contravariance. These concepts are always seen together. They basically mean that when one thing grows, another thing will shrink, and that opposite changes will always balance out. A lot of physics classes put a lot of emphasis on vector components, which are the numbers that describe a vector. You might see the components written as an ordered pair, or written in a column like this. But it's important to remember that vector components are only half the story. We also need to pay attention to the vector basis, which are basically the measuring sticks that we use to get the vector components. Basis vectors and vector components are like two sides of the same coin. We can never deal with one without also dealing with the other. It's very important to remember to think of basis vectors and vector components together, because when we change coordinates, we'll see that both the basis vectors and the vector components change, and also that they change in opposite ways. Let's consider this pencil sitting on the table here. If we measure it using the EX and EY basis vectors, we find that the pencil is equal to 1 EX vector and 1 EY vector. The components are 1 and 1. But now let's take a look at a new basis, EX tilde, which is twice the length of EX, and EY tilde, which is twice the length of EY. This means that to construct the pencil, we only need 1/2 of EX tilde and 1/2 of EY tilde. The components are now 1/2 and 1/2. The important idea here is that when we made the basis vectors twice as big by multiplying by 2, the pencil vector components shrunk in half by multiplying by 1/2. The pencil is equal to both of these vector expressions, but in order to maintain the equality, the basis vectors had to grow and the vector components had to shrink. Let's look at this idea again by taking the EX and EY basis vectors, and this time by making them twice as small, with the new basis vectors being EX with this smile shape above it, and EY with the smile shape as well. Now, to construct the pencil, we need 2 of EX smile and 2 of EY smile. This time, the basis vectors shrunk in half, and the vector components needed to double in size in order to balance out and maintain equality. So you can see that when one thing grows, the vector components, another thing must shrink, the basis vectors, in order to maintain the balance. So we see that basis vectors and vector components behave in opposite ways. When basis vectors grow, the components shrink, and when basis vectors shrink, the components grow. For this reason, we call basis vectors covariant, and we call vector components contravariant. Vector components do the contrary or opposite thing that basis vectors do, and this is why they are called contravariant. So let's take a closer look at what's going on, using the original basis EX and EY, and the basis that's twice as long, EX tilde and EY tilde. Let's start with the expression 1EX. It's perfectly fine to multiply by the number 1 in the middle of this expression, since multiplying by the number 1 doesn't change anything. Now let's take this number 1 in the middle and split it into 1/2 times 2. The numbers 1/2 and 2 are opposites and multiplied to give the number 1, so we haven't changed anything. Now let's multiply the components by the 1/2 and multiply the basis vector by 2. And of course, doubling the length of the EX basis vector just gives us the EX tilde basis vector. So we see that this equals 1/2 EX tilde. So here we can definitely see that the basis vectors were multiplied by 2 and the vector components were multiplied by 1/2. But since the growing and shrinking balance out, 1EX is still equal to 1/2 EX tilde. If we write out the full expression for the pencil vector, we can do this again. We can insert the number 1 between the vector components and the basis vectors for both x and y. Then we can split the number 1 into 1/2 multiplied by 2. We find that the components shrink to half as big, and the basis vectors grow to be twice as long. And since the tilde basis is twice as long as the original basis, we can write 2ex as ex tilde and rewrite 2ey as ey tilde. The pencil is equal to both of these expressions because we are free to grow the basis vectors as long as we shrink the components. Let's go through this one last time, but using array notation. We can write the pencil vector expression 1ex plus 1ey as an array multiplication, where the row of basis vectors is multiplied by the column of vector components. We can get back the original expression using the multiplication rule I talked about earlier. First entry times first entry plus second entry times second entry. Now, if you know linear algebra, you know that we can always multiply by the identity matrix with ones along the diagonal and zeros everywhere else without changing anything. The identity matrix is a bit like the number 1, because multiplication by the identity doesn't change anything. Next, we can split the identity matrix into two parts, a matrix with 2's along the diagonal and a matrix with 1/2 along the diagonal. These matrices are opposites, or inverses, and they multiply together to give the identity, so we haven't changed anything. Now, this array multiplication with the basis vectors just ends up multiplying the basis vectors by 2, so we can rewrite this row as ex tilde ey tilde. And this array multiplication just multiplies the components by 1/2, so we can rewrite this as the column 1/2, 1/2. And if we multiply these arrays using first entry times first entry plus second entry times second entry, we get 1/2 ex tilde plus 1/2 ey tilde. So again, we can see that growing the basis vectors and shrinking the components balances out, and the pencil can be equal to either of these expressions. Now, so far, I've been giving the specific example of scaling basis vectors and components, making them bigger or smaller. And to do that, I've used a change of basis matrix to scale the basis vectors, and a change of component matrix to scale the vector components. As long as the growing of one and the shrinking of the other balances out, we don't end up changing the vector. But the ideas of covariance and contravariance don't just apply to scaling. It can apply to any type of transformation. For example, if we rotate the basis in one direction, the components will rotate by the same amount in the other direction. Also, if we shear the basis in one way, the components will shear in the exact opposite way. In general, the change of basis matrix on the left and the change of component matrix on the right will always be inverses of each other, and they will multiply to give the identity matrix, which again ensures that the result vector does not change. Later in this video series, we'll see that Galilean relativity is really just changing time and space coordinates using a Galilean matrix, as seen here, where the Galilean matrix for the basis vectors is the opposite of the Galilean matrix for the vector components. And after that, we'll see that special relativity is really just about changing the time and space coordinates using a Lorentz matrix. Again, changing the basis vectors in one way and changing the time and space components in the exact opposite way. We'll see that using this Lorentz matrix can explain time dilation, length contraction, and all the other strange things that Einstein predicted. When something transforms like basis vectors do, using the change of basis matrix, we say that thing is covariant. We generally will be writing covariant things as rows. And when something transforms in the opposite way, using the change of component matrix, we call that thing contravariant. And we will be writing contravariant things as columns. So originally, we said that covariance and contravariance was all about this idea of one thing growing and another thing shrinking, and the opposite changes balancing out. To be more specific, when we change basis vectors in one way, a vector's components will change in the exact opposite way. These opposite changes will balance out, leaving the vector unchanged. So to sum up Relativity 102, there were two key ideas. The first idea is invariance. Invariance tells us that we can have the same physical object, which is not changing, and therefore invariant, described in different ways, using different coordinate systems. For example, this pencil vector has components 1, 1 in the EX, EY basis, but it has components 1/2, 1/2 in the EX tilde, EY tilde basis. The pencil is invariant, but the components can change. The second important idea was the idea of covariance and contravariance. These ideas tell us that when the basis vectors change in one way, the vector components must change in the opposite way. For example, when writing the expression for this pencil vector, we can make the basis vectors twice as big, and in exchange, the vector components must become twice as small in order to balance out and make the equal sign still valid. Remember that basis vectors and vector components are two sides of the same coin. We can never deal with one without also dealing with the other. A coordinate transformation will change both the basis vectors and the vector components, and they will change in opposite ways in order to maintain balance. I just want to repeat that if you're confused by these past couple videos, that's totally fine. We're going to be covering invariance, covariance, and contravariance in more detail in later videos. I just wanted to show them as soon as possible to prepare you for what's coming up next. Next, in Relativity 103, we'll discuss Galilean relativity.